Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. In today's video we will learn all about the basics of NPN transistors. From symbols and definitions, through terminology, all the way up to reading and understanding datasheet, so in this video there is going to be everything you need to know to start using NPN transistors in your circuits like a professional. So, let's get started. Let's start with basics, the definitions. NPN transistor is one type from a large group of what is called bipolar junction transistors. Bipolar junction means that transistor is composed of one P region, sandwiched between two N regions, hence the name, NPN. In previous videos we know that P region is an intrinsic silicon crystal doped with impurities, so that it becomes positively charged, or simply put, it has excess of holes, the positive carriers. Analogous to P region, the N region is intrinsic silicon crystal doped with impurities, so that it becomes negatively charged, or simply put, it has excess of electrons, the negative carriers. As bi means two, and polar means opposite sides, the word bipolar in the name simply says that there are two N-type regions on the opposite side of one P-type region. The word junction in the name means that there are also two contact points, or fancy name for this is junctions, between top and the middle region, the NP junction, and between middle and bottom region, the PN junction. So, one would wonder why is it not called bipolar bijunction transistor, but whoever was in charge of naming things in electronics deserves a VIP place in hell, and if there is no hell, there should be one for these guys. Nothing in naming schemes makes sense to newbies, and each term is a minefield of its own. No wonder why people find electronics so difficult to learn. Next thing on our list are symbols. Symbols are the way to graphically represent NPN transistor in drawings. On the left-hand side we have a block diagram symbol. This way of representation is commonly used when presenting and explaining different parts of semiconductors regions, such as P or N-type regions, and how they relate to each other. In the middle, we have an electronic circuit symbol for NPN transistor. You can draw it with, or without the circle, it is up to you, but be consistent. The most important thing when drawing NPN symbol in electronic circuits is orientation of the arrow pointing the flow of the base current. From previous video we have learned that depiction of arrow tells us that base current is flowing from base terminal into the transistor, where it adds up with collector current, and as a result we have emitter current. For both block and electronic circuit symbols, the connecting terminals are called base and emitter, and they are denoted with letters C, B, and E. Connecting terminals are used to connect the transistor with other components in the circuit. And finally, on the right-hand side we have 3D model of the transistor. In factories, the transistors are made in all various type of form factors. This one is called 292. They can also come in MD form factor, which stands for surface mounted device, or 120, and many others. Now it is time to name currents flowing in and out of NPN transistor. If you previously dealt only with electric components that have two terminals, or connecting points, such as resistors, capacitors, diodes, and etc., you are familiar that there is only one current running through the component. Since transistors have 3 points of contact with rest of the circuit, now situation complicates a little bit more, but not so much. On screen, we have our NPN transistor symbol, with collector, base and emitter terminals properly marked. Current going from power source into collector terminal is called current collector, and it is marked with yellow arrow, pointing direction of the current in the circuit. The current going from power source into base terminal is called base current, and it is marked with red arrow. Please note, and we repeat again, because it is very important, the direction of base current is from power source into the NPN transistor. Both current and base currents are going from positive terminal of power source into NPN transistor. Now, inside the transistor itself is where the magic happens. Both collector and base current adds up, and the sum of those current is what is called emitter current. So, the current flowing out of transistor, through emitter terminal is called emitter current. As emitter current is sum of collector and base current, we get first most important formula for NPN transistors, which says that emitter current is a sum of collector and base current. This is very important, so please make sure to learn this by heart. Please note that we are using what is called conventional or engineering direction of flow of current, from positive to negative terminal of power source. Now, there is also a fourth current, called the base cutoff current, but we will get to that later in this video. Now, this gets a little bit confusing for beginners, so let's draw equivalent scheme on the right-hand side, but only depicting currents, so that you visually comprehend what is going on. As stated before, inside of NPN transistor is where magic happens. Inside, both collector and base currents get added together, and leave the transistor through emitter terminal. Next logical question is, from where do these currents come from and how we determine how much of each current we need or want? Let's draw a proper schematic of electric circuit consisting of one NPN transistor and power source. For power source, let's use a simple 1.5 volts battery. The proper way to connect the NPN transistor is to connect collector to positive terminal, and emitter to the negative terminal of battery. Also, we need to add what is called collector current limiting resistor, to prevent too much of current flowing in the transistor. If we omit this resistor, then transistor will pull as much current through the collector, as power source can provide, and then transistor will overheat and burn out. Please remember to never, under any circumstances, connect transistor to power source without collector current limiting resistor. This is very important. Now, you would expect that our battery will happily provide power and start powering the transistor. No. There is no current now running through the transistor. But why? Well, that is how the transistors are designed. It is not enough to just provide power to collector terminal, we also have to power the base terminal as well. Only collector and base terminal properly powered, the transistor will function as expected. This is how the transistors are designed and made to operate. In order to make our transistor work, we need one more battery. This one will provide necessary power to base terminal, so that our transistor can function. Now, as same as with the collector terminal, we should never power base terminal from battery directly, without resistor. This resistor is called the base resistor, and he plays the most important role in any circuit containing NPN transistor. Again, never, under any circumstances, connect the base to the battery without base resistor. If you omit this resistor, the base terminal will draw as much power as it can from battery, it will overheat, and the transistor will burn out. Please remember to never, under any circumstances, connect transistor to power source without base current limiting resistor. This is very important. Now, calculating values for collector and base limiting resistors, as well as values for power sources, depends on whether we want to use transistor as a switch or as an amplifier. So, this naturally brings us to next chapter in our video, function of the transistor, or you can also call it, mode of work. Depending on the choice of power source in general, and collector and base current limiting resistors in particular, the NPN transistor can function in one out of two modes, as a switch or as an amplifier. The mode of work is determined by how much of current goes into base terminal. In one of the previous videos, we saw that if base current is 0, or is less than some value A, predetermined by the design of the transistor itself, then no current flows through the transistor. If this is the case, we call this mode, the cutoff mode, or simply said, the transistor acts like an open switch. Now, if base current is greater than some predetermined value B, then transistor functions as a closed switch, and we say that transistor operates in saturation mode. In this scenario, the current running through the collector is limited only by collector current limiting resistor. If the base current is between values A and B, then transistor functions like an amplifier. But what does transistor amplify? Good question. If we want to use transistor as an amplifier, we also need to provide an AC signal for transistor to amplify. Now, there are two scenarios. In first scenario is in amplification mode, and there is no AC signal present, then collector current will be proportional to base current. This coefficient of proportionality is called DC current gain and is marked as beta. In second scenario, when there is a presence of AC signal, the collector current will be proportional to the sum of base current and AC signal current. In this case, this coefficient of proportionality is called small signal current gain and is marked as HFE. Now, if you listen to all of this gobbledygook in previous chapter, and still trying to wrap your head around what this all means, struggling to make heads and tails out of this nonsense, you are absolutely in the right frame of mind. For last 75-ish odd years, give or take a year or two, transistors have been taught and explained to pupils and students like this. From our own personal experiences, we can testify that after listening to this lecture in formal educational facility, more than 110% attendees left the classroom understanding absolutely nothing about transistors. The overflow of 10% refers to people who were passing by in the street, and were as baffled as the ones sitting in the classroom. This is nonsense, this is stupid, this makes no sense, and this is not how transistors should be explained. No wonder why so many people have justified fear of transistors in particular, and electronics in general. The educators, especially those with masters and PhDs, go out of their ways to complicate this subject as much as they can. We have no kind words for those experienced electricians as well, with decades of on-hands experience in building amplifiers and circuits with transistors. They are just as bad as anyone else. This doesn't have to be this complicated. Now that we have vented one more pet peeve, out of endless number of pet peeves, and grudges, that we hold against electronics establishment and elites, let's explain this in simple and easy to understand way. Let's bring back our circuit and let's see how we can simplify this, so that anyone can understand it. First of all, we need to plug in some numbers, so that we can get sense of values for resistors and currents in the circuit. For this video, we have chosen the widely used and very popular NPN transistor 2N3904. We also downloaded datasheet from the manufacturer website, so let's look at the maximum ratings. We need to know what is the maximum current we can safely run through our transistor. We are looking for maximum allowed collector current. Knowing the voltage of the power source, by using Ohm's law, we can easily calculate the value for collector current limiting resistor RC. From the datasheet we can see that maximum allowed collector current is 200 milliamperes. So, plugging in values for current and voltage, we get that collector current limiting resistor is 7.5 ohms. Now, word of warning. These values are for demonstration purposes only. Do not try to build this schematic in real life. Resistor of 7.5 ohms, under 200 milliamperes of current, would burn out in an instant. It simply cannot dissipate that much of heat. When we get to real-life examples, we will plug in safe values for voltage, current and resistors. For now, all we need to know is that collector current has to be 200 milliamperes or less. Now, chasing those predetermined values of A and B for the base current is colossal exercise in futility. When we want transistor to be in cutoff mode, we do not want any current flowing into base terminal. So, for the purposes of sanity, and for all other purposes, when we want transistor to be in cutoff mode, then base current is equal to 0. There is no more to it than that. If base current is 0, then our transistor acts like an open switch in the circuit. Let's draw equivalency schematics. On the left-hand side, we have our circuit, without any power to base terminal. So, when base current is equal to 0, the left-hand side schematics is equivalent to the schematics on the right-hand side. We can replace transistor with mechanical switch in the open position. Since the circuit is broken, no power can run through it, so this also means that collector current is also 0. In order not to omit any important information about NPN transistor cutoff mode, we have to declare that there is a theoretical value, for the value of A, for the base current, when the transistor is still in cutoff mode. That value is so small, it measures in nanoamperes. Those values are in range of 10 to the power of -9. In real-life scenarios, this is unmeasurable with any measuring device available to a common person. So, for all purposes, we are happily ignoring it, and moving on. Next item on the list is finding the value of B for the base current, when our NPN transistor is in saturation mode, or simply said, when it functions like a closed switch in the circuit. For this task, we need to bring back our circuit, and we also need to bring back our datasheet. But this time, we are looking for section in the datasheet named, on characteristics. We are looking for value of base current for which the transistor goes in the saturation mode. Let's zoom in the datasheet section, and try to find parameters we are looking for. We are looking for values for base and collector current, for which transistor goes into the saturation mode. Remember that we must not exceed maximum value for collector current of 200 mA. And that contains collector emitter saturation voltage, that says, if we have base current of 1 mA, and collector current of 10 mA, then our transistor goes into saturation mode of work, and functions like a closed switch in the circuit. There is also another line, that gives us a pair of two more values for base and collector currents. So, let's get back to our circuit, plug all these values in, and see what value resistors do we need to drive our transistor into saturation mode of work. In first case, from datasheet we have values for base and collector current of 1 and 10 mA, respectively. We know that out power source is 1.5 volts, so, by using Ohm's law, we can get values for collector and base current limiting resistors. We get values for our C equals 150 ohms, and for our B we get 1.5 kiloohms. For second case, we have values for base and collector current of 5 and 50 mA respectively. Plugging in the numbers, we get values for our C equals 30 ohms, and our B equals 300 ohms. Let's draw an equivalency schematic for this scenario. On the left-hand side, we have circuit with base current of 1 or 5 mA. We have calculated and adjusted values for collector current limiting resistor to 1.5 kiloohms and 300 ohms, respectively, so that we can get 10 and 50 mA of collector current, respectively. When these conditions are met, our transistor is in saturation mode, and functions like a closed switch in the circuit. One important thing to notice is that our collector currents in both cases are well under maximum allowed value of 200 mA. Of course, a simple logical question pops out immediately: why would we want transistor in the circuit when mechanical switch can do exactly the same thing, without all these complications with transistors, resistors, currents, and etc.? Well, the obvious answer is that we want to eliminate human input. A switch must be switched on and off by a human, and this is fine for certain scenarios, when you want to switch the light on or off, turn the water heater on and etc. Now, somewhere in our daily lives we all saw some blinking lights, like warning signs, or just decorative light that periodically goes on and off. Imagine that poor human who has to sit for 8 hours daily, and mechanically switch the lights on and off. That is where transistors come in play with a role as a switch. By adjusting base current, we can literally switch something connected to the transistor on or off, without any human input. That something we are turning on or off in transistor circuit is called the load. That is just fancy name for anything we connect between power source and collector terminal. Next question is, where does that switching on and off current comes from? Well, it comes from something called signal generators, if we want periodical switching, or it can come from photodiodes. Mechanism of every door that automatically opens when you approach them, consist of some sort of diode that senses your presence, and transistor that switches on and opens the door via some internal mechanism. Transistors in a roll of switch are everywhere around us, even if we don't see them in plain sight. Earlier in the video, we briefly mentioned that beside collector, base, and emitter current, there is also fourth current flowing through the transistor, the base cutoff current. If you watched our video about diodes, it's episode 7 of this series, then you may be familiar with this topic. In short, the story goes like this: if you flip the diode in a circuit, or to be ultra sciencey, if you reverse bias the diode, there is a small current flowing through the diode. Diode biasing refers to the application of an external voltage across a diode to control its operation. It essentially determines whether the diode will allow current to flow or block it. With an ideal diode, if you reverse bias the diode, or just flip it the other way around, no current should flow through the circuit. That is the function of the diode, to allow current to flow in only one direction. However, in real world, there is no such thing as an ideal component, hence, there is no ideal diode. If you flip the diode, there is still a small current flowing through the circuit. That current is called reverse current, or IR. For common rectifier diode, this current is in range of 10 to 50 microamperes. We can check the datasheet for the details. Now, you may wonder, what has this all got to do with transistors and base cutoff current? At the beginning of this video, when we talked about the symbols for NPN transistor, we mentioned block diagram symbol, so let's bring it back. We also defined a NPN transistor as P-type region, sandwiched between two N-type regions, hence the name NPN transistor. Sometimes, in order to simplify the explanation of workings of transistor, an equivalency scheme is drawn with two diodes, where two diodes are placed in series. Please beware that in real life, if you place two diodes like this in your circuit, you will not get a NPN transistor. This model of transistor, with two diodes, is just for explanation of base cutoff current purposes only. By definition, the base cutoff current is the current flowing from emitter to collector terminal, when voltage is applied across collector and emitter, but there is no voltage at the base terminal. So, this would be a same scenario as when NPN transistor is in cutoff mode, or simply put, when it acts like an open switch. So, let's bring back all the schemas, and see what is going on in here. Let's connect the battery to our two-diode model of transistor. Now in this configuration, the diode D1 is reverse biased, and diode D2 is forward biased, in relation to the battery. From previous videos about diodes, we know that forward biased diode conducts current, with very small voltage drop of 0.3 or 0.7 volts, so, we can go one step further and replace this diode with an equivalency resistor, RBE. The abbreviation comes from fact that this equivalency resistor is between base and emitter terminals. Now, this equivalency RBE resistor will play important part in our future videos, when we talk about transistor as an amplifier. But in this scenario, we are not interested in specific values of resistor RBE, nor its specific function in this type of circuit. When sufficiently high voltage is applied across collector and emitter terminals, this resistance becomes negligible, so it can be discarded, and another equivalency scheme can be drawn, without resistor at all. So, what we are left with, in this circuit, is a simple reverse biased diode. From everything we have learned before, we know that when diode is reverse biased, there is always some small current flowing through it. In this scenario, when we are dealing with transistor, this diode reverse current is called the base cutoff current. So, even when there is no base current present, a small, but insignificant current runs through the transistor, so the transistor, in true life, is never an open circuit when it is in cutoff mode. If we go back to our circuit scheme, in order to be compliant with what is truly going on in the transistor, we have to add a dashed line in equivalency scheme, so that we acknowledge that there is a current present in the transistor circuit, albeit very small and insignificant, but still there. The symbol for base cutoff current is IBL. So, in circuit with transistor acting like a switch, even if there is no base current present, there is always some small current running from collector to emitter terminal. For all practical purposes, this IBL, or base cutoff current, is discarded as negligible, and we consider transistor in this mode as an open switch. A quick look at the datasheet of characteristics gives us value of 50 nanoamperes, when collector-emitter voltage is 30 volts, and base current is 0. Please have in mind, that for this particular type of transistor, the maximum allowed collector-emitter voltage is 40 volts. So, from datasheet, we infer, that for all practical purposes, we should not exceed 30 volts for collector-emitter voltage. There is also another current, the collector cutoff current. But, when transistor is in switch mode of work, this current plays no role, so for now, we will disregard this parameter as unimportant for our work. In this part of the video, we will talk about transistor as an amplifier. At the beginning of the video, we have learned that, depending on value of base current, the transistor can have two modes of operation, as a switch or as an amplifier. If base current is 0, or is greater than some predetermined value, transistor operates as a switch. That predetermined value is defined by design parameters, and it is not same for all transistors, so you have to consult datasheet for specifics. On the other hand, if base current is greater than 0, and less than that same predetermined value B, then transistor acts as an amplifier. So, to simplify it, if base current is in that Goldilocks middle, not too high, not too low, then transistor is in amplifier mode of work, and if base current is 0 or too high, then transistor is in switch mode of work. As simple as that. Now, the most obvious question that follows is, what does transistor amplifies? In many books dealing with transistors, and in most videos, there is just this stupid sine wave line, without any markings, values, or any indications what it might represent. It is just drawn in every schematic, and we are all left with that eternal question, who needs to amplify sine wave line in first place, and if there is a reason to make it bigger, why don't you just draw a bigger sine wave line? Nobody tells you what is the reason why it is there, or what it represents. Is it a current, is it a voltage, is it extraterrestrial communication from aliens, or is it just that malicious streak from electronics elites, deliberately not explaining things in comprehensible way? You can guess what we think, and leave the answer in the comments section of this video. Let's dispatch with the most obvious stupidity. The sine wave line is just a symbol for input signal. Why not square, saw or triangle shape of the signal? Nobody knows. Someone, just out of uttermost malice, determined that symbol for input signal in amplifiers will be sine wave line, and left it like that, without any definition or explanation. Now, amplifying any of these basic types of signals is an exercise in futility. If you have means to generate these signals in the first place, for example, by using signal generator, you should be able to generate signals of desired amplitude, without any need for amplification. Generate the signal of desired amplitude and shape in the first place, and be done with it. Now, that we have vented another of our pet peeves, let's get on with the video. In truth, amplifiers were there to amplify audio signals, in the beginning, or later on, both audio and video signals. Now, most newbies think that amplifiers amplify sound. No, sound is mechanical wave propagated through air. Amplifiers amplify only electric signals. For example, the most basic way to generate audio signal is via microphone. By definition, microphone is a device that transforms sound into electrical signal. Now, problem with microphones is that they generate very weak signals, and if we would to play that signal through loudspeakers, we wouldn't hear anything. That is why we need amplification, to amplify weak signals. There is nothing more to it than that. Next, ambiguousness with sine wave line is what it represents, current or voltage. What do amplifiers amplify? Well, to play devil's advocate, amplifiers amplify electric signals. Now, there you have it. Joke aside, if you watched out previous videos, you have learned that current, voltage and resistance cannot exist without each other. That is Ohm's law. It comes in three ways, each one defining relations between current, voltage and resistance. So, we can choose to observe input signal either as a voltage or as a current, but the design of an electrical circuit needed to amplify current differs greatly from the one needed to amplify voltage. Depending on your needs, you either design amplifier to amplify current or voltage. You cannot amplify both voltage and current simultaneously by using just one transistor. Let's draw two basic schematics for transistor as an amplifier. On the left-hand side you have a basic current amplifier. On the right-hand side, you have basic voltage amplifier. You can see that circuit design differs significantly, depending on whether we amplify current or voltage. That circuit for transistor as a current amplifier, the one on the left, looks identical to circuit for transistor as a switch. That is because, amplifying current is just matter of avoiding that the sum of current of input signal and base current, equals to 0, to avoid driving transistor in cutoff mode, or sum of input signal current and base current, being too high, then driving the transistor into saturation mode. Amplifying current is matter of finding that Goldilocks value of sum of base current and input signal current, so that we drive transistor into amplifying mode of work. As for the voltage amplifier, that is just whole another world. In voltage amplifier, the base current also needs to be in that Goldilocks range of values, and that is determined by the value of resistor R1, but in addition to that, the overall voltage that is a sum of signal voltage and voltage across resistor R2, needs to be in resistor to amplify the input voltage signal. And there is also that damned capacitor C as well, as things were not complicated enough already. We will make separate videos, explaining amplifying current and voltage. For now, you need to be aware that amplifying current and amplifying voltage are two very different circuit designs. Reason for amplification is to make weaker input signal stronger, regardless whether we have weak current or voltage input signal. Next on the list is something called biasing the transistor. There is endless number of explanations, lectures, schematics and whatnot, explaining biasing of the transistors. And guess what, they are all useless. Poor souls, trying to understand the incomprehensibility of transistors, as explained by elites, are driven to tears and verge of insanity by useless stupidities, such as tinkering with values of base current, or applying 0.65 or 0.7 or God forbid 0.8 volts, across base emitter junction, like we are supposed to know what base emitter junction is, in the first place. Explaining biasing of the transistor, without context of mode of work, or simply put, explaining biasing without explicitly saying are we using transistor as a switch, or as an amplifier, is the most deliberately malicious, evil, and ill-intended complication to make transistors as difficult as possible to understand. The way to correctly bias transistor depends only, and only upon, the selected mode of work and nothing else. In simplest of terms, biasing the transistor means applying correct values for voltage and current at the base terminal. When we want transistor to act as switch, we will calculate one set of voltage and current at base terminal, and when we want to use transistor as an amplifier, we will calculate different set of values for current and voltage to be applied at the base terminal. We choose mode of work, we have appropriate formulas, and calculate desired values for voltage and current. As simple as that, biasing explained. At the beginning of this video, in details, we have explained three different currents flowing through the transistor circuit: collector, emitter, and base current. Later on, we also mentioned a parasitic base cutoff current that messes with transistor when it is in cutoff mode of work. Now, we also need to do the same with voltages. Voltages applied at collector, emitter, and base terminals also play an important role in the way transistor behaves and operates. Although, the base current is what primarily defines transistor's mode of work, we would be negligent, and our video incomplete, if we omit to define and name voltages in transistor circuit. First, we would like to invite you to watch first 4 episodes of this season, as they explain in detail everything you need to know about differences of potentials, voltage, and reference values. These are prerequisites in order to fully comprehend what we are about to talk from now on. By definition, voltage is difference in potentials of two different points in the circuit. Voltage must be always referenced to something. We cannot just say 5 volts, as by the definition itself, 5 volts can be difference between 5 and 0 volts, or it can be difference between 195 volts. If reference is omitted, by convention the voltage is referenced to the ground. Again, by convention, ground point is assigned value of 0 volts, just so that the calculation would be easier. Again, we most kindly invite you to watch further episodes of this season, as all of this is explained in detail. Now, let's put back symbol for NPN transistor, and recognize all 3 terminals: collector, base and emitter. More often than not, in these kinds of explanations, the ground point is omitted from the circuit, it is assumed, but not drawn, so let's fix that omission, as we need ground point to reference our voltage names. Now, since emitter terminal and ground share same point, when you are referencing voltages in NPN transistor circuit, you can interchangeably reference them to the ground or emitter point. It makes no difference, unless there is a resistor between any of the terminals. First voltage is something called VCC. It is a supply voltage, shared between collector and base terminal. The abbreviation VCC stands for voltage at the common collector. It simply means that collector and base terminal are attached to the same power source. Having 2 different power sources, one for base terminal, and the other for collector terminal, would unnecessarily increase complexity, and increase cost of implementing the circuit. So, it is common practice that base and collector terminal share the same power source, where current is regulated by appropriate resistors. Next, we have voltage between base terminal and ground, called VB, and voltage between base and emitter terminal, called VBE, unless there is a resistor RE present, these 2 voltages are the same. In circuits where transistor is in switch mode of work, or acts like a current amplifier, the resistor RE does not exist, and both VB and VBE voltages have the same value. When transistor is in amplifier mode, the resistor RE is present, and these 2 voltages are now different. Next, we have voltage between collector and emitter terminal. Now, this voltage is very specific. You might have already guessed that we had mentioned this voltage before. If transistor is in saturation mode, this voltage is approximately 0.2 to 0.3 volts. We explained that resistor RC always has to be present, otherwise, the transistor will burn out. When we want to measure VCE voltage, we place multimeter probes below RC and above RE resistors. If resistor RE is omitted, when transistor acts like switch or current amplifier, then VCE and VC are the same. Now, when circuit design requires all 3 current limiting resistors to be present, RC, RB and RE, there are also additional voltage drops across two of these resistors. There is voltage drop across our C resistor, before collector terminal, and there is, also, voltage drop across our E resistor, after emitter terminal. You will notice that we do not mention voltage drop across our B resistor. Since our B resistor plays specific role in regulating current to base emitter, the voltage drop across this resistor plays no role in this configuration, as we are only interested in current going into base terminal. There is a specific formula for calculating value for resistor RB, where VCC and VBE have specific predetermined values. Now, depending on your circuit design, you can have multiple resistors, multiple capacitors, even diodes, and whatnot, in your transistor circuit. It is very important to name all the nodes in the circuit, or simply set every connection point between different electronic components, and name voltages and currents accordingly. This is a mark of the professional. The last thing left to do, is to give a quick overview of NPN transistor datasheet. Now, we have already covered some of the transistor parameters from the datasheet. We will make a separate video going through all of the parameters and explaining each one in the details. For this video we will just name sections that will help you navigate and find operational parameters for the specific design you wish to implement. In this video, our transistor of choice is ubiquitous NPN silicon general purpose transistor 2N3904. In general, every transistor datasheet will cover following group of parameters: maximum ratings, thermal characteristics, and group of parameters called electrical characteristics. Each group of parameters have a name that is pretty self-explanatory, but let's go through each one of them in order of appearance on datasheet. Maximum ratings represent group of parameters that refer to maximum voltage, current and ambient temperature, that we can apply in circuit design using this specific transistor. These are by no means recommended values of current, voltage and ambient temperature, but rather maximum values that transistor will tolerate for a short period of time, before burning out. It is a sound advice that you have the values for voltage and current from this group of parameters, if you want to play it safe and have your transistor working for a long time. Thermal characteristics refers to transistor's ability to dissipate heat, and tells us how much degrees of Celsius transistor temperature will rise, with every watt of power dissipated. Electrical characteristics represent a bunch of parameters divided in 4 groups. Each group addresses parameters related to the specific mode of work. The first group is called off characteristics, and it refers to parameters when transistor is in cutoff mode of work. As we have learned, cutoff mode is analogous to an open switch. Next group is called on characteristics, and it refers to parameters when transistor is in saturation mode, or when it is in amplification mode, but without input signal present. Next group, called small signal characteristics, refers to parameters when transistor is in amplification mode with small AC signal present at the base terminal. This group of parameters is very important when we are using transistor in amplification mode. And the last group of parameters is called switching characteristics. These parameters refer to transistor's ability, how fast it can go from cutoff to saturation mode and back. In real life, it tells you about frequency limitation of specific transistor. And there you have it, NPN transistor explained as simply as possible. We would like to take this opportunity to say thank you to all of you who have subscribed to our channel. Special thanks go to all of you who have left comments and inquired about our videos, or just posted interesting questions of your own. Your kindness in communication and the time you have chosen to spend watching our videos is greatly appreciated. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time. Bye.